In this video, we'll use factorial and double factorial as coefficient of the exponential distribution function. We begin with the value of lambda, which is equal to data validation, list of items, 0 to 0.5 to 2. So these are values of our lambda. Next, the data set of the probability density function, which is array formula, EXPONDIST of the x values, comma, and our lambda will be this value, and 0 because this is a probability density function. So for now, we'll have lambda at 0.5. We continue with the cumulative distribution function, which is array formula, EXPONDIST of the x values, where lambda, this is our lambda, comma, 1, which is cumulative distribution function. And the Taylor-Maclaurin series sum of both, where you have the summation of x raised to the power n plus k, where the value of k is data validation, list of items, 0 or 1. And say, if k equals 0, then it is the probability density function. If it is 1, it will be cumulative distribution function. And RA is the factorial form and the double factorial form. And the value of n will be from 0 to infinity. In this case, 16 is good enough. Now we continue with the factorial form of the coefficient. So RA formula, minus 1 raised to the power n. That's the first item, times lambda raised to the power the quantity n plus 1. So lambda raised to the quantity n plus 1. N plus 1. All over the denominator, which is factorial n plus k. So factorial n plus k. Then enter. We continue with the double factorial, which is equal to array formula, minus 1 raised to the power n. Second item, times lambda raised to the power the quantity n plus 1. So n plus 1. So we have completed the numerator. Now the denominator. There are two parts, double factorial and double factorial. So factorial, double factorial, and plus k. That's a double factorial. The second part, also double factorial, but there is a minus 1. So we just copy the first few items here, copy. So we multiply times and paste. This time there's a minus 1, so we subtract 1. Minus 1. And enter. So at k equals 0, you have an error. So we have to correct this. So this will be if n equals 0, then it should be lambda. So to correct that, you have a condition if n, that is G3 to G19 equals 0, then lambda. This will be lambda. Then enter. So if we assign 0.8, this will be 0.8. And these values are the same. Now we can continue with the expansion, which is array formula, SERIESSUM of the x values raised to the power n plus k, where n plus k starts from n, increment starts from k incremented by n. So this is k incremented by n, where n is 0, 1, 2, 3, so the increment is 1. And the coefficient, we can start with the factorial. Let's start with the factorial for now. And these values are the same because k equals 0. If k equals 1, these values are the same. We'll chart this. So insert chart. And we will use scatter chart. Use the scatter chart. And for the series, you show the trend line polynomial to the 6th degree and use the equation as label. For the legend, position at the bottom. In the case of the yellow, there's no yellow in the data set, so we replace that with green. Change this color to green. And for the rest, all series, our point size will be large, maximum. Except for the expansion, the point size will be none. But since there's none, the thickness of the line will be maximum, so that you can toggle. Next, we calculate this polynomial regression coefficient using the LINEST. To do that, we complete the LINEST matrix, starting with the power. Transpose 0 to 6. Continue with the elements of the matrix. So array formula of the x values raised to the power 0 to 6. And enter. Now we can calculate the coefficient. So array formula or LINEST data y and data x. Then enter. Second part is the expansion. LINEST data y and data x. And finally, something's wrong. This one here is okay. This one here. Oh, this should be data x. Then enter. And finally, the cumulative distribution function, LINEST, data y, and data x. Enter. We can inspect if our calculations are correct. Begin with the x to the 0. That's 0.8. This is 0 times 10 to the minus 33. This is 0. X, the x coefficient, 0.64. And then 0.8 and 0.8. X squared coefficient, 0.256, 0.32, minus 0.32, and minus 0.32. X cubed coefficient, 0.0676, 0.0845, 0.0845. So it's negative 0.0676. And the x to the 4th, it's 1.29 times 10 to the minus 2. That's 0.0129. And this is 0.161, 161 times 10 to the minus 2. And the x to the 5th coefficient, that's 1.69 times 10 to the minus 3, 2.11 times 10 to the minus 3, and 2.11 times 10 to the minus 3. X to the 6, 1.14 times 10 to the minus 4, minus 1.43 times 10 to the minus 4, and minus 1.43 times 10 to the minus 4. So we can start with point 0.5. At 0, the blue and the red are linear. So the expansion approximates the probability density function. If you toggle it to 1, k equals 1, then the expansion approximates the cumulative distribution function. And their polynomial regression coefficients are the same. If we go 0.8, so the red and the green are the same, meaning the expansion approximates the cumulative distribution function. Toggle it to k equals 0, then the expansion approximates the probability density function. Suppose I use, instead of the factorial, I will use the double factorial. Let's see what happens. Enter. The dataset remains unchanged. They're the same. Their polynomial regression coefficients are the same. We can increase that to 1. So the expansion approximates the probability density function. Toggle it to k equals 1. The expansion approximates the cumulative distribution function. Let's say this is 1.25. So they're the same. They're still the same. So they're the same. And the datasets are the same. Toggle it to k equals 0. These datasets are the same. The polynomial regression coefficients are the same. This completes the use of double factorial in generating the Taylor-Maclaurin series sum of EXPONDIST or exponential distribution function.